These are the Module 1 notes on function notation. First, we will discuss properties of functions. So a function is a rule that produces a correspondence between two elements, and we often describe functions using equations. Recall that an equation has two algebraic expressions, so often we describe them as a left side and a right side, where they are equal to each other. Now consider the equation for the area of a rectangle with width 1 inch less than its length. If we define x to be the length of the rectangle in inches, then the area y is given by the following equation. Recall that the formula for area of a rectangle is length times width. We know that the length is represented by x, and the width is 1 inch less than the length, so we can represent that using x minus 1. And of course, because the width must be a positive value, we need to restrict the values of x to be greater than 1. In this particular equation, variable x is called the independent variable, and variable y is our dependent variable. So independent variables are variables that do not depend on anything else, whereas dependent variables depend on another variable. So to find the value of y, we must use the value of x, therefore y depends on x. When two variables are related through an equation or function, we can represent the numbers as an ordered pair. For example, with our equation for the area of a rectangle, if we define the length, so if x is equal to 5, then we can calculate the value of y. We find that if the length is equal to 5, then the area of our rectangle is equal to 20, and we can express that as an ordered pair. And our ordered pair xy is equal to 520. Notice the first value in our ordered pair is our independent variable, which we can also consider our input. And then the second value is your dependent variable, y, which is the output of the equation. And it depends on our independent variable. So for example, if a bank pays 8% interest per year, then the worth, which can be expressed by the variable w, of an investment of p dollars after 1 year would be w is equal to 1.08 times p. So to calculate the worth for any initial investment p after 1 year, we can use this equation. If p is equal to $100, then w is equal to 108. So in other words, if we initially invest $100, we will have $108 after 1 year. That can be expressed as the ordered pair of variable p. W is equal to 100 and 108. It's worth noting that we looked at the Cartesian coordinate system and ordered pairs when we were studying linear equations in Math 145. In particular, we looked at graphing ordered pairs from a table of values to graph a linear equation. Now we're going to look at f of x notation, or function notation. Suppose that we had two relationships to track that use the same variables. For example, function 1, or relationship 1, where y is equal to 2x plus 1, and a second relationship where the same variable y is equal to x squared plus 2x minus 3. We can use different letters such as F or G to denote names of the equations. And we also see that it makes it very clear in our notation that the functions both depend on the same independent variable x. So using function notation, we can write that f of x is equal to 2x plus 1, and g of x, our second relationship, is equal to x squared plus 2x minus 3. In these notations, you can see we are replacing y with f of x in the first equation and y with g of x in the second equation. It's worth noting that this is not f times x, it is a function f defined for variable x. And what we can do is we can set a value for x and find the corresponding value of the function. Now we can determine what the value of the function of f of x is when x is 2. This boils down to finding the value of function f at 2. And so what we do is replace the x in our function with the value of 2 everywhere where an x appears. Often we perform the substitution in brackets so that we know that multiplication is occurring, and we ended up getting the value of function f at 2 is equal to 5. If we want to list this result as an ordered pair, we can write it as the ordered pair x and f of x is equal to, so our input variable was 2 and our output was 5. So function notation is very useful when you're finding the value of your function for several values of x, and especially when you want to remember the relationship between your input and output variables. A more precise definition of a function than was previously given is that a function of a single variable x is a rule f that assigns each value of x to another number f of x. That's called the value of the function at x. We can examine this visually or graphically by considering your input variables along a horizontal axis and your output values along a vertical axis. And for each input value of x, we can plot the value of f of x, which is y. And we can plot each of these points. So for a particular x value, whatever your y value or f of x value is equal to. And then we can plot the function as either a set of points or a line that, say, connects each of these values. I like to think of functions as being this magical, we can call it just a magical box. So we can call this function, our function f of x. We have input values, and our input values are all of our independent variables, so our x values. We put it into the function, and within the function, a mathematical calculation, whatever rule is defined by f, is performed, and then we get our output values on the other side. And these output values are all our f of x values. In Math 145, we looked at linear equations. With linear equations, we had values of x, which represented the values that went into the function, and then we calculated a value of y, which was really functions, just not written in function notation, where we calculated the y value for each value of x. Now we're going to look at evaluating functions. In Math 145, when we created a table of values for various values of x and calculated the value of y, we really were evaluating functions for particular values of x. Here we're going to evaluate the function f of x is equal to 1 over x at a point. So we specify a value of x, then we find the value of the function by dividing 1 by that number, since the rule is that f of x is equal to 1 over x. So for example, if we have x is equal to 2, then f, our function evaluated at x equals 2, is 1 over 2, or 1/2. We can also evaluate our function at a variable. So instead of using x is equal to some number, we can replace x with another variable, such as a. So f at a is equal to 1 over a. Similarly, f of x plus h can be written as 1 over x plus h. So anywhere that we had an x in our original function is replaced with whatever is in the brackets using our function notation. In this example, we're going to look at 3 different functions and evaluating them at different values. So we have f of x is equal to 12 divided by x minus 2, g of x is equal to 1 minus x squared, and h of x is equal to the square root of x minus 1. In example A, we want to evaluate f at x for x equals 6. So this becomes 12 over 6 minus 2, 12 over 4, or 3. Therefore, our function f of x evaluated at 6 is equal to 3. Written as an ordered pair, we could write this as x, so our input and our output is equal to 6, 3. Writing the ordered pair was not necessary here. I was simply wanting to point out how it would line up with a graphical representation of this function. So g of x is equal to 1 minus x squared if we evaluate it at x equals negative 2. When we substitute a negative number, you want to make sure, or really any substitution, it's helpful to be done in brackets. And you can see here how important that is, because when we square a negative number, you end up getting positive 4, and the final answer is negative 3. With part C, we're evaluating h at negative 2. So h of x is equal to the square root, and we substitute a negative 2 for x, and we end up getting the square root of negative 3, which is undefined. You can't take the square root of a negative number, therefore h, our function h, is not defined at x equals negative 2. In part D, we're looking at f at 0 plus g at 1, and we're subtracting h at 10. What we need to do is plug in the individual values of x into their respective functions. So when we plug in 0 into f, we get 12 divided by 0 minus 2, and then g of x, get 1 minus 1 squared, and lastly h at 10, we have the square root of 10 minus 1. Make sure your square root line goes over the entire function as shown in the original function h. And when we perform this calculation and simplify, we get negative 6 plus 0 minus the square root of 9, which is negative 6 plus 0 minus 3, and our final answer is negative 9. Now make sure you practice doing this on your own. There are textbook questions with references available on D2L, as well as a digital homework quiz to allow you to practice problems like this.